In this next video, we're continuing our discussion on zeros and factors of polynomials. So let's just review a few of the properties of polynomials that we've already discussed. One of them is that if a is a zero of the polynomial, then we know a factor of that polynomial, and that factor would be x minus a. If that a0 has a multiplicity, so if a is a zero with multiplicity of m, then the factor would show up m number of times, so x minus a to the m power must also be a factor of the p of x. The degree of the polynomial helps us understand how many zeros there should be. So a polynomial of degree n has exactly n zeros as long as we're counting the multiplicities. If it has a multiplicity, then it does add up to the actual degree. So for this example, x minus 2 cubed times x plus 1 squared, this is a degree 5 polynomial. If we were to expand this all the way out into standard form, that leading term would be x to the 5th power. It is degree 5, and it has a 0 at x equal 2, and this happens 3 times. That's because that's a multiplicity of 3. The 0 at negative 1 is counted 2 times because it has a multiplicity of 2. The last property that we haven't really touched on is if the polynomial has real coefficients and if a plus bi is a 0. So this time we have a complex root. Then a minus bi is also a 0. So those complex roots always come in a pair, and it's because we're doing this plus or minus the square root of a negative number thing. That imaginary part comes from doing the square root of a negative, and that would only happen with that plus or minus. So we want to find how do I factor all of these polynomials, and how do I find the roots? So we've been given a polynomial p of x, x cubed minus 4x squared plus 9x minus 36. The first thing we want to do is factor into a product of linear factors and irreducible quadratic factors. This is a degree 3 polynomial, so it's a cubic function, and it has 4 terms. That hopefully gives you a clue that we're going to need to factor by grouping, or at least try. So I'm going to group the first 2 terms and the last 2 terms, and take p of x, write out your GCF in the first pair, that's x squared. So that first pair would be x squared times x minus 4. Then we look at the second pair. 9x minus 36 has a GCF of 9. That would be plus 9 times x minus 4. Because these x minus 4s match, we do have a common factor of x minus 4. So we can write p of x as x minus 4 times x squared plus 9. This is a product of a linear factor and an irreducible quadratic factor. This x squared plus 9 cannot factor more. So x minus 4 is our linear factor, and x squared plus 9 is your irreducible quadratic factor. If that's all it asked us to do, which is the first part, then we're done. This is part of the answer. But there is a second half to this question. It says then, so there's part 1. Then we want to factor this completely into all linear factors, with complex coefficients. So for part 2, to get all linear factors, we need the zeros. So let's find those roots first. We already know that x minus 4 equals 0. It gives me a root at positive 4. That part is a linear factor. We're used to that. The x squared plus 9, we would solve that for when it's equal to 0 by subtracting 9, taking the square root of both sides. That leaves me with plus or minus the square root of negative 9. There's our light bulb moment. That square root of negative 9 is going to be an imaginary number. So we have plus or minus 3i. The other two roots were imaginary. It's because it's coming from this irreducible quadratic factor here that gave me the square root of negative 9. So the roots for 3i and negative 3i can be written as a product of linear factors. This would be x minus 4, x minus 3i, and x minus negative 3i. Remember, if a, let's move this down, if a is a 0, then x minus a is a factor. So if 3i is a 0, then x minus 3i is a factor. If negative 3i is a 0, then x minus negative 3i is a factor. Now we wouldn't typically leave it that way because x minus a negative seems weird, but x minus 4 times x minus 3i times x plus 3i is a product of linear factors, and they have complex coefficients. We would call this root form of that polynomial. Now, a common question is, how can I factor a polynomial if it won't factor by grouping? So we've had different strategies for factoring, and one of the new ones is factoring by grouping. But the answer to that question is that we wouldn't know. We would have to know some other root of the polynomial, either by given a graph or just by being told one of the roots, so that we could use it to find other factors. So for number 2, we've been given a polynomial p of x is x cubed minus 5x squared plus 17x plus 123. And we want to determine which one of these is a 0, negative 4 or negative 3, and then factor completely into linear factors with complex coefficients. Now we've had some similar examples to this, but we didn't have imaginary numbers that came out of it. So when we were trying to determine which one of these is a 0, you could use division, or that remainder theorem says that the remainder is still going to be the exact same value as evaluating the function. So if I do p of negative 4 versus p of negative 3, we can determine which one of these is a 0. So that's negative 4 cubed minus 5 times negative 4 squared plus 17 times negative 4 plus 123. And then we do the same thing with negative 3. Negative 3 cubed minus 5 times negative 3 squared plus 17 times negative 3 plus 123. And we just plug those straight into our calculator to see what this comes out to be. Remember to put the parentheses around your value when you're plugging this in, especially when we're doing that negative 4 squared part. So when I plug in negative 4, I got negative 89. That tells me automatically that negative 4 is not one of the zeros. But we better check negative 3 because I could have made a mistake in typing this in, or maybe neither one of them is a 0 and then we're kind of stuck. But negative 3 to the third minus 5 times negative 3 squared plus 17 times negative 3 plus 123 does give me a 0. So x equals negative 3 is a root or a 0 of p of x. Which means that x plus 3 is a factor. Since it's a factor, then we can use division to help factor this polynomial. We just needed to figure out what one of the zeros is first. So we're going to use either long division, or if you know synthetic division, you can still do that with this. We are just really sticking with this long division concept. We divide this out. So go ahead and finish out your long division, and I'll do mine. All right, this is the tedious part of the video. Sorry. And remember, you can use a calculator. Don't worry if you have to, but we're doing, in this one, 17 minus negative 24. That might be harder to do, but it does give me 41. Hopefully you do get a remainder of 0. And that shouldn't really be surprising since we knew that x plus 3 was going to be one of the factors. But that helps me figure out that p of x could be written as x plus 3 times x squared minus 8x plus 41. Now this is a linear and irreducible quadratic factor since that does not factor more. But we want to factor this completely into linear factors with complex coefficients. So to get the complex coefficient part, we need to find the roots. So remember, to get all the linear factors, we need to find the roots. We find them by setting the factors equal to 0. X plus 3 equals 0, we already know is going to give me a root at negative 3. X squared minus 8x plus 41 equals 0. We have to use the quadratic formula for. So x equals negative b, negative negative 8, plus or minus the square root of b squared minus 4ac. So in that case, it would be plus or minus the square root of negative 8 squared minus 4 times 1 times 41 all over 2a, so 2 times 1. That has 8 plus or minus the square root of something divided by 2. We just have to figure out what is that something by plugging this in. And it gives me negative 100. So we're taking the square root of a negative. That's automatically going to be an imaginary number. The square root of negative 100 would be 10i, so 8 plus or minus 10i over 2 gives me the zeros 4 plus or minus 5i. And I really need some extra space here. So I'm just going to add this to a second sheet of paper here. If I know the zeros, then I can use those zeros to write out the polynomial in factored form. So p of x is x plus 3 times x minus of 4 plus 5i and x minus a 4 minus 5i. We had 3 roots, one at -3, one at 4 plus 5i, and one at 4 minus 5i. If we take that and write the factors, the linear factors, look like this. You can go ahead and distribute that subtraction. This form is not wrong, and that would be perfectly fine for me. But we could also write that as x plus 3 times x minus 4 minus 5i, if we distribute the subtraction there. And then distributing the subtraction again gives me x minus 4 plus 5i. So either one of those would be a valid form. You just might see the second one as the actual answer on an answer key. So let's go ahead and pause there, and then we'll start back up in another video.